Hello, everyone, and welcome to the lecture on carboxylic acid derivatives. Okay, so this is chapter 20 in the third edition of David Klein, and it's entitled Carboxylic Acids and Their Derivatives. So carboxylic acids are pretty stable and found in nature commonly due to important hydrogen bonding that happens with them. You can see that small molecular weight carboxylic acids don't smell very good, which is in contrast to other functional groups like aldehydes and esters, which tend to have a much more pleasant smell. You can see acetic acid is the acid in vinegar, and vinegar doesn't have a very pleasant smell. Butanoic acid is responsible for the rancid odor of sour butter. You can smell the essence of dirty socks if you smell hexanoic acid, and then lactic acid, which is produced in our bodies, that makes our muscles sore, and it's responsible for the taste also of milk after it's gone sour. Carboxylic acids are also important in pharmaceuticals. You can see aspirin has a carboxylic acid derivative, and also in other important molecules that treat tuberculosis and acne. So in terms of nomenclature of carboxylic acids, what you want to do is count the carbon chain. Don't forget the carbonyl carbon. So this would be a 4-carbon chain. Normally we would name that a butane, but because of a carboxylic acid at the end of the carbon chain, we would drop the E and add the suffix oic acid. So instead of butane, it becomes butanoic acid. Carboxylic acids have a very high priority in terms of nomenclature. They have a higher priority than, for example, alcohols. So we would give priority to the carboxylic acid, name the molecule as a carboxylic acid, and also start the locant at the carboxyl carbon, which would be this one, right? And then count towards the longest carbon chain, including the alcohol functional group. And this would end up 5-hydroxy 4,4-dimethyl pentanoic acid. So because a carboxylic acid is always a terminal functional group, it's always going to be assigned the locant position number 1. So we don't need to include a 1 locant when we're naming something as a carboxylic acid, because it's assumed that it would be there. When you are naming a carboxylic acid that is attached to a ring, you name the ring as an alkane and then add the term carboxylic acid. So this becomes cyclohexane carboxylic acid. There are many common names for simple carboxylic acids, such as formic acid and acetic acid, propionic acid. And just so you know, in IUPAC, these would also have names. This would be methanoic acid, ethanoic acid, and propanoic acid. So it's often confusing because propanoic acid and propionic acid are actually very similar names, but one is IUPAC derived and the other one is a common name that's IUPAC accepted. We also have butyric acid, also known as butanoic acid, and benzoic acid, which you guys have seen before. Dicarboxylic acids are named with the suffix dioic acid after the carbon chain. So for example, because this is a 5-carbon chain, we would name this pentane and then with the suffix dioic acid. Some dicarboxylic acids have common names because they are, well, common. And you'll see these names periodically pop up various places. For example, oxalic acid, you may have remembered in the lab, we looked at chemiluminescence and we used oxalyl chloride, which is the diacid chloride derived from oxalic acid. Malonic acid, you're going to see this again in chapter 21. Succinic acid, this would have a 4-carbon chain. Glutaric acid is important biologically. Let's do a practice problem. Go ahead and try to provide an IUPAC name for the following compounds. If you'd like, pause it so you can give yourself some time, and then we'll talk about the answer. Okay, so hopefully you came up with 2-methylpentanoic acid. I got that by starting my locant counting here at 1, 2, 3, 4, 5. Right, so there's a substituent and methyl group at carbon number 2. Because this would be a pentane, right, we drop the E and add the oic acid. So 2-methylpentanoic acid is what we come up with. This one is slightly more complicated because it contains both a ketone functional group and a carboxylic acid functional group. Recall that carboxylic acids have a pretty high priority. And so ketones would fall as a lower priority group and get named as a substituent to the carboxylic acid. So again, we'll start our counting here, 1, 2, 3, 4. At this point, we could go down this direction or this direction, but we want to get the oxo group in the parent. So we will go over here to carbon 5 and carbon 6. So then we end up with an isopropyl substituent and an oxo substituent. I comes before O alphabetically, so it becomes 4-isopropyl, 5-oxo hexanoic acid. If you'd like to practice nomenclature further, refer to conceptual checkpoints 20.1 to 20.3 in your Klein textbook. Their next part of the textbook talks about structure and properties of carboxylic acids. In the past, I've created a video on this section, so I'll just link that video here so you can watch it separately, or you can watch it as part of the PowerPoint slides if you have access to those, since it is embedded in these slides and this video. Let's review the reactions that have produced carboxylic acids that we've encountered prior to this chapter. In chapter 9, we saw that we can do ozonolysis on alkynes, and we end up with cleaving the carbon-carbon triple bond and getting carboxylic acids. So if these two R groups are identical, there would only be one product, and that would be ideal. In addition, if this was a terminal alkyne, then we would actually only get one carboxylic acid and a molecule of carbon dioxide. We can also oxidize primary alcohols to a carboxylic acid. We originally encountered this reaction in chapter 12. It takes a strong oxidizing agent to do that, such as sodium dichromate. We can also oxidize the benzylic carbon as long as there's at least one hydrogen attached. We can use sodium dichromate to oxidize it to a carboxylic acid, specifically a benzoic acid. Let's look at some new reactions that produce a carboxylic acid. The first reaction we're going to look at is the hydrolysis of a nitrile. So if you were to access a nitrile, you can do acidic or basic, actually, hydrolysis, and this will be explored a little bit later on in this chapter. It takes a lot of heat to hydrolyze a nitrile, but with sufficient heat, you can synthesize the carboxylic acid. So for example, one way we've seen the synthesis of nitriles in the past is through an SN2 reaction with an alkyl halide and, for example, sodium cyanide. Recall with SN2 reactions, it's preferable to have a very unhindered alkyl halide, so this ideally is methyl or primary. Also note that in this synthesis, we have added one carbon to the organic substrate. So this benzylic bromide has a total of 7 carbons. Notice that when we do our SN2 reaction with cyanide, we introduce another carbon, right? So we've added a carbon and now we have 8 carbons in the structure. So this is sometimes called a 1-carbon homologation reaction. A second method to produce carboxylic acids is from a Grignard reagent. And instead of treating a Grignard reagent with an aldehyde or ketone or ester, which we've seen in the past, you could also treat it with carbon dioxide, which is typically obtained from dry ice. The Grignard reagent will do a nucleophilic attack on the carbon in carbon dioxide, and a resonance arrow will move electrons up to one of the oxygens. A carboxylate will be produced. We need an acidic workup in order to isolate the neutral carboxylic acid. Notice that this is also a 1-carbon homologation reaction because we are adding the carbon from carbon dioxide. This is another synthesis where we start with now bromobenzene, treat it with magnesium in an ether solvent to form the phenyl magnesium bromide Grignard reagent. From there, we can treat with carbon dioxide, followed by an acidic workup to obtain benzoic acid. Notice how this carbon does not have to be unhindered or primary in order for the synthesis of this carboxylic acid. So this actually is a second alternative to producing a carboxylic acid, but it's also more general. Because with the first method using sodium cyanide, we needed a methyl or primary alkyl halide due to the inclusion of an SN2 reaction. But this reaction doesn't require an SN2 reaction, and therefore we're able to get away with non-hindered alkyl halides. And in addition to that, it's okay for the carbon to be sp2. So we're able to form carboxylic acids where the carbon attached to the carboxyl carbon is actually sp2 in addition to sp3. Let's do a practice problem to make sure we're truly understanding this concept of the different methods for synthesizing a carboxylic acid and when they would be successful. So the question is, which of these reactions would be unsuccessful as written? So for example, if you would not expect to get this product, right, given these reagents, you would put a big X through it, okay? There may be more than one of these 3 reactions that are unsuccessful. Go ahead and pause the video and think about which ones you think are unsuccessful. Think about reasons why, and then we'll talk about it. Okay, so this top reaction is actually an unsuccessful reaction. If you notice, the carbon, the alpha carbon to the halide is sp2. So that means we cannot use the sodium cyanide method of producing a carboxylic acid because we cannot do an SN2 reaction on an sp2 hybridized carbon. However, we can form a Grignard using this alkyl bromide, in this case, alkenyl bromide, and produce a carboxylic acid. In addition, the bottom reaction would not work as written. And the reason why is did you catch the fact that the reactant and the product both had 4 carbons? Remember that both of these reactions are 1-carbon homologation reactions. So we should actually be producing a 5-carbon carboxylic acid from a 4-carbon alkyl halide. If you want to practice this further, check out Conceptual Checkpoint 20.10. Okay, what else can we, so now we're going to start talking about reactions of carboxylic acids. Carboxylic acids can be reduced to primary alcohols with lithium aluminum hydride. So here's a carboxylic acid. Notice the reagents are lithium aluminum hydride followed by an acidic workup, and we're able to completely reduce the carbonyl and synthesize a primary alcohol. The mechanism is actually different for this reduction than the corresponding ester analog. With a carboxylic acid, when we treat this with LAH, the hydride will first act as a base to deprotonate the acidic hydrogen in the carboxylic acid, producing a carboxylate. Luckily, the carboxylate continues to react with the aluminum with 3 hydrides attached. It does a 2+2 cycloaddition reaction with this carbonyl, forming this tetrahedral intermediate. Notice that the aluminum is still coordinating to one of the oxygens, and it actually makes it a good leading group. As a result, it can leave, and we can form a carbonyl as this leading group gets kicked out, and we're able to access an aldehyde through that process. And as we know, aldehydes can be further reduced to primary alcohols using lithium aluminum hydride. So we would need another equivalent of LAH to do the reduction of the aldehyde. And this is a review mechanism from the alcohol chapter. Hydride does a nucleophilic attack on the electrophilic carbonyl carbon of the aldehyde, and a resonance arrow moves electrons up to the oxygen. That forms a now tetrahedral carbon with an alkoxide. After acidic workup, we're able to isolate the neutral alcohol. Another reagent that can be used to reduce a carboxylic acid down to a primary alcohol is borane. Borane can actually be used instead of LAH, and it's actually chemoselective for reduction of the carboxylic acid. This is a key term you want to know. Chemoselective means a reaction that operates exclusively on one functional group in the presence of other functional groups. So for example, the chemoselectivity of borane can be observed through the reduction of this para-acetyl benzoic acid compound. If we treat this with borane, it will selectively reduce the carboxylic acid down to a primary alcohol, even in the presence of a ketone. You should be thinking this is quite noteworthy because ketones are actually much more electrophilic than carboxylic acids. So if we were to treat this with any other reducing agent, such as sodium borohydride or lithium aluminum hydride, the ketone would be reduced, right? And it gets reduced typically faster than carboxylic acids because of its enhanced electrophilicity compared to carboxylic acids. The reason why borane is able to be chemoselective is that the boron actually needs to coordinate to both oxygen atoms of the carboxylic acid to then deliver its hydride and reduce the carbon. Because the ketone only has one oxygen, the important coordination is not possible and ketones are not reduced. Notice that I've been talking about the reduction of the carboxyl carbon down to primary alcohols, right? If we were to calculate the oxidation number, it would be a true reduction of that carbon. But there are many reactions where you're converting a carboxylic acid to another functional group and we don't change the oxidation state. For example, if we just substitute the hydroxyl group of the carboxylic acid for a different group, we'll call this a heteroatom, so maybe some oxygen, nitrogen, or halogen-based group. The oxidation state does not actually change because this is still a electronegative atom, and the electrons would be assigned to this atom when calculating oxidation number. So we're going to look at a variety of reactions where we're able to convert a carboxylic acid to different functional groups. Because there's no change in oxidation state, we call these carboxylic acid derivatives. The most common carboxylic acid derivatives are an acid chloride or halide, an acid anhydride, an ester, and an amide. You can see that these also look the most like a carboxylic acid because they still have a carbonyl like a carboxylic acid. Notice that the heteroatom here is chlorine, oxygen, again oxygen or nitrogen. Because these are all more electronegative than carbon, the electrons are assigned to these heteroatoms and there's no oxidation state change if you were to convert a carboxylic acid to any of these functional groups. In addition, nitriles are also considered a carboxylic acid derivative because the carbon is bonded 3 times to an atom that's more electronegative than it, and it has the same oxidation state. Acid chlorides, or halides in general, and anhydrides are actually not very commonly found in nature because they are pretty reactive and relatively unstable. Esters and amides are the more stable of the carboxylic acid derivatives, and so therefore found more commonly in nature. For example, these naturally occurring esters here can be found in different flowers and fruits, and they tend to have a very nice smell. Amides are also very common because of their stability. They are, you can see that they are the part of the backbone of the structure of proteins. In addition, you can find amides in various natural products, such as melatonin, which is used as a natural sedative. Let's talk about nomenclature of these carboxylic acid derivatives. If we were naming an acid halide, we're going to, and with all the carboxylic acid derivatives, what I want you to do is think about how you would name the compound if it was a carboxylic acid, and then just change the suffix appropriately. So a carboxylic acid with 2 carbons can either be called ethanoic acid or acetic acid, and acetic acid is much more common. To then change it to an alkyl bromide, we're actually going to replace the ic acid and change the suffix to -il, followed by the halide that's present. So it becomes acetyl, in this case, bromide. Benzoic acid is also another common name for a carboxylic acid. We can again remove the ic acid and add the -il, in this case, chloride. Recall that if we have a carboxylic acid directly attached to a ring, we call this a cyclohexane carboxylic acid. To change it to an acyl or acid halide, we're going to come up with the same substituent, cyclohexane, followed by the term, instead of carboxylic acid, carbonyl chloride. Anhydrides are typically made from carboxylic acids as well through a dehydration process. If it's a symmetrical anhydride, we can just simply think about the carboxylic acid that it came from, think of the name of that, in this case acetic acid, drop the word acid and add the word anhydride. Because succinic anhydride comes from the dehydration of succinic acid, we can just take the common name succinic acid and change it to succinic anhydride. We can also have asymmetrical anhydrides, in which case it has 2 carboxylic acids that were responsible for its synthesis, right? For example, benzoic acid and acetic acid. So we would put both of those terms, drop the acid and add the word anhydride. Make sure to place these in alphabetical order. To name an ester, the first part of the name comes from the group attached to the oxygen side of the ester. So because this is an ethyl group, we're going to write the word ethyl first. The rest of it comes from the root of the carboxylic acid. So think about the fact that this ethyl acetate came from acetic acid, right? If we name acetic acid and we want to change it into an ester, we're going to drop the ic acid and add -ate at the end. So it becomes ethyl acetate, which is a common organic solvent. Here's another common name, malonic acid. It's a dicarboxylic acid. So when it gets converted to an ester, we need the term diethyl, and then we drop the ic acid and add the -ate, so it becomes diethyl malonate. The same rules apply if there is an alkyl group directly attached to the ester. just think about how you would have named the carboxylic acid, in this case cyclohexane carboxylic acid. And because it's an ester, we're going to drop the carboxylic acid and add the term carboxylate. And don't forget the methyl, right, which is like a substituent of the carboxylic acid derivative. So it goes in front. So it becomes methyl cyclohexane carboxylate. Let's talk about amides. How do you name amides? Well, we're going to drop the suffix-ic acid, and in this case, add the suffix amide, right? So acetic acid becomes acetamide. If you end up with an oic acid, we actually drop the O as well. And so this benzoic acid becomes benzamide. If the amide is directly attached to cyclohexane, we're going to call it cyclohexane carboxamide. What about if the nitrogen has one or more substituents? We actually describe those substituents by using N. N is like a locant. Think of it as like a number, 1, 2, 3, 4, but instead of using a number, we're going to call the locant the nitrogen. So this becomes N-methyl, right, or a substituent on the nitrogen, which is a methyl group. And then again, think of how you would name this carboxylic acid. It would be acetic acid, so it becomes acetamide. If there's two substituents and they're the same, we can do N comma N and then di, whatever the group is, in this case, dimethyl. The last of the carboxylic acid derivatives is the nitrile. To add a nitrile, we're going to drop the suffix ic acid or oic acid and add O-nitrile. So acetic acid then becomes acetonitrile, which is a common organic solvent. And benzoic acid becomes benzonitrile. Let's do some practice with some naming of a few of the carboxylic acid derivatives. Go ahead and pause the video and attempt to come up with the IUPAC name, and then we'll talk about it. Okay, so hopefully you notice that this is an anhydride. So it's going to be named with the last word anhydride. In order to figure out what should come first, we need to think about the carboxylic acids that were used to form the anhydride. So imagine that this was a carboxylic acid and come up with the name. We would number 1, 2, 3, 4 and come up with 3-methyl butanoic acid. And again, in order to change an acid to an anhydride, we just drop the acid and add the word anhydride. So then this becomes 3-methyl butanoic anhydride. What about this ester? So recall that we can name this as a carboxylic acid and then change it into an ester. So dropping this heptyl group, we're going to go ahead and name this part of the molecule as a carboxylic acid. The longest carbon chain, starting with carbon number 1 here, is a 5-carbon chain with a 4-methyl group. So this becomes 4-methyl pentanoic acid. In order to make this into an ester, we're going to drop the ic acid and add 8, right? So this becomes then 4-methyl pentanoate. But don't forget the oxygen side substituent, right? Count up the number of carbon, in this case 7. So we're going to name that as another substituent, or heptyl 4-methyl pentanoate. What about this amide? Think about where the carboxylic acid can be found in the amide. If we change this nitrogen to an OH, we end up with acetic acid as our base acid. So again, to name an amide, we're going to drop the ic acid and add the word amide. So acetic acid becomes acetamide as the parent. It also has 2 substituents on the nitrogen. It has both a methyl and a benzyl. B comes before M alphabetically, so we go N-benzyl N-methyl, followed by the word acetamide. In order to get some more practice, please look at the Klein book and do conceptual checkpoints 20.12 to 13. Let's start talking about the reactivity of carboxylic acid derivatives. We're actually, just for simplicity, going to leave the nitrile out of this list and just look at the acid chloride, anhydride, ester, and amide. You can see that the acid chloride is the most reactive, followed by the anhydride, and the most stable, like we talked about before, the ester, followed by the amide. The reactivity is determined by several factors, including induction, resonance, steric hindrance, and quality of the leaving group. Let's look at the most reactive and the least reactive and using these factors determine why their reactivity. Okay, so the acyl chlorides, also known as acid chlorides, are the most reactive of the carboxylic acid derivatives. If we look at the induction, the halogen is pulling electron density away from the carbonyl carbon, making it more electrophilic. Of course, the oxygen is also pulling electron density away through the sigma bond. This is also induction, but it's common to all of the carboxylic acid derivatives that we're comparing, so we're just ignoring that for now. In terms of resonance, we do think the chlorine donates electron density into the empty p orbital of the carbonyl group through resonance, but it does so fairly insignificantly. And again, that's because the p orbitals are going to be mismatched in size. The carbon has a 2p orbital and the chlorine will use a 3p orbital. Because the 3p orbital is much larger than a 2p orbital, there's insufficient orbital overlap, and this type of contribution is fairly minor. As a result, induction is pulling electron density away and resonance is not donating it back to any significant extent, creating a significant positive charge on the carbonyl carbon. Let's look at amides. These are actually the least reactive of the derivatives. When we look at induction, the nitrogen atom is less electronegative than chlorine or oxygen. So it's not pulling electron density through the sigma bond away to the same extent. However, resonance is different. The lone pair on the nitrogen atoms donates significantly into the empty p orbital of the carbonyl carbon. It does so because now we have a matched p orbital size. Both carbon and nitrogen will use a 2p orbital, and due to being the same size, there's significant orbital overlap, and now this is a much more significant contributor. As a result, the positive charge here is not as significant or as positive to the same degree or extent as with the acid chloride. Notice I didn't talk too much about the other two factors, sterics and quality of the leaving group, and that's because they can vary, right? Some of these have R groups, so we don't know what size those are. As the group gets larger, there's going to be more steric hindrance, and that will make the carbon less reactive towards nucleophilic attack. And otherwise, there isn't a significant difference, for example, between the size of a chlorine and a nitrogen, so it wasn't really mentioned as one of the most significant factors. In terms of quality of the leaving group, both the chloride and the carboxylate are the best leaving groups. Recall that good leaving groups are weak bases, and chloride is a very weak base. In contrast, its conjugate acid, HCl, is a very strong acid. Okay, let's talk a little bit about the difference between carboxylic acid derivatives and aldehydes and ketones, which we studied in the previous chapter. We noted that aldehydes and ketones are also electrophilic at their carbonyl carbon, right? But they don't undergo the same reactions as carboxylic acid derivatives, because carboxylic acid derivatives have a group that can function as a leaving group. So they're able to undergo nucleophilic acyl substitution reactions. We can't do a substitution reaction with an aldehyde or ketone because hydrides and carbides do not function well as leaving groups. because they're not stable and they're not weak bases. So carboxylic acid derivatives undergo a type of reaction which we call a nucleophilic. This refers to the reagent that gets added, right? We always name the reaction after the reagent, not the substrate. So it is a nucleophilic acyl because this is considered an acyl group, right? An acyl substitution where we are substituting whatever heteroatom Z is with a new nucleophile. Let's look at the general mechanism. It has two core steps. From the carboxylic acid derivative, we can have, if we treat this with a nucleophile of sufficient strength, it can do a nucleophilic attack on the electrophilic carbon. We can show a resonance arrow to move electrons up to the oxygen in order to avoid exceeding the octet on this carbon. That produces a tetrahedral intermediate that then goes through loss of a leaving group to expel the best leaving group, in this case Z, and regenerating a carbonyl in that process to get a neutral product. Overall, it is a substitution with a nucleophile. It is not an SN2 reaction, so we don't call it an SN2 mechanism. Instead, we call it a nucleophilic acyl substitution, also sometimes drawn as SNAC. Also, just note again, if this was a hydrogen, we cannot kick out hydride, right? It's not a good leaving group, so we don't kick out hydrides. So this cannot be a hydrogen. In addition, it cannot be a carbon, because if we kick out a carbon, we're essentially kicking out a carbanion. Again, carbanions are strong bases, not weak bases, so they make terrible leaving groups. Let's look at a specific example of a nucleophilic acyl substitution reaction. In this case, we have an acid chloride, and the nucleophile is methoxide. So we can do nucleophilic attack, right? In order to avoid exceeding the octet, we can move electrons up to the oxygen. That gets us our tetrahedral intermediate. At this point, the best leaving group will leave. Chloride is a far better leaving group than methoxide because it's a far weaker base. So chloride will get expelled along with reformation of the carbonyl group, and in the end, we've synthesized an ester from an acid chloride, also known as an acyl chloride. Please understand that this mechanism is not an SN2 process, so we should not be drawing a mechanism consistent with an SN2 reaction, which is a concerted one-step reaction. We understand that the acyl substitution is at minimum a two-step process. Remember that when drawing mechanisms, it's important to think about the conditions employed, think about whether or not any proton transfers will be necessary, and just note that under acidic conditions, negative charges rarely form, and under basic conditions, positive charges rarely form. Okay, so again, when we're thinking about mechanisms, make sure that the reactants, the intermediates, and the leaving groups, which are all the participants in the reaction mechanism, they should be consistent with the conditions employed. So for example, make sure you look at what's over the arrow. In this case, this is an acid catalyzed reaction. So any mechanism that we draw should be consistent with acidic conditions. That means that intermediates are either neutral or have one positive charge. Negative charges rarely form under acidic conditions. Let's think about the first step. We might think that water, which is our nucleophile, will do a nucleophilic attack on the carbonyl of an ester. But this is not likely to be the case for multiple reasons. First of all, esters are pretty stable, right? They're not as stable as amides, but they're one of the more stable carboxylic acid derivatives. And water is also neutral and stable. So both of these are neutral, which means, again, no formal charge, and fairly stable. So if they were to react together, we would expect a fairly high activation energy for that step. because we're going from two stable reactants to an intermediate that has formal charge. In this case, both a positive and a negative formal charge. So this is going to be a very high activation energy barrier. So it's very unlikely that the molecules will have enough energy to do this reaction without significant heating in the reaction mixture. But recall that the reaction was acid catalyzed. So the first step under an acid catalyzed reaction is likely going to be protonation of the carbonyl. You might ask yourself, why isn't this oxygen protonated? Well, it could be protonated, but proton transfers are usually reversible. So even if we were to proton transfer to protonate this oxygen, it can also, that same proton can also be removed and go back to the ester. When we draw out the resonance contributors of an ester, what we'll notice is that this oxygen has a partial positive charge, and this oxygen has a partial negative charge. So it actually makes more sense that this oxygen is more electron rich, so it is more basic, and it is the likely oxygen to pick up a proton from hydronium ion, which would be present from aqueous conditions where there's an acid catalyst present. So proton transfer then produces the protonated carbonyl. That's going to make this carbon much more electrophilic, and so it's very reasonable intermediate to form. At this point, we have a much more reactive organic intermediate because there's a full positive charge. The energy of that has been raised significantly from before it gained a proton and it was neutral. So then when water does a nucleophilic attack to form the intermediate, it's not as high of an energy gap, right? Because we're going from one of our substrates has a positive charge to an intermediate with only one positive charge. So the difference in the energy of these is not likely to be as great as we would have seen had we done nucleophilic attack prior to proton transfer. Let's look at how the reaction might proceed under basic conditions. Under basic conditions, we're going to have some hydroxide present. Hydroxide is a much better nucleophile than water, so it's much more likely that hydroxide will act as our nucleophile in preference to water. Hydroxide has a full formal negative charge, so it's much more reactive than water. As a result of our nucleophile being more reactive, that raises the energy of our substrate nucleophile combination, such that the combination of the two is now higher energy, and going from one negative charge on an oxygen to an intermediate with a negative charge on the oxygen is not going to be significantly different in energy. So we're going to have a very reasonable activation energy for this step. So when you have a strong nucleophile like hydroxide, you can just go ahead and directly do a nucleophilic attack in the first step of the mechanism, move electrons up to the oxygen to avoid exceeding the octet on this carbon, and move on with the mechanism from this intermediate. Let's think about what is likely when there's an amine present instead of an alcohol. When there's an amine present, any acid present will just protonate the amine because the amine is basic. Unfortunately, ammonium ions are not acidic enough to protonate the oxygen of an ester, so it's unlikely that that's going to be the first step in our mechanism. Instead, we can just use the amine to do a direct nucleophilic attack on the carbonyl. In this case, we are going to have a fairly significant activation energy barrier because, again, these are neutral and this is charged. However, amines are more nucleophilic than alcohols, so overall, they're a little bit higher in energy than alcohols, so the activation energy is a little bit lower than it would have been with water. However, even though the activation energy is a little bit lower, it's still pretty significant, and this is a pretty slow reaction. As a result, organic chemists would not likely do this reaction because it would require a prolonged period of heating, and instead, if they wanted to use an amine nucleophile, they will just choose a more reactive carboxylic acid derivative, like an acid chloride. We talked about the fact that we may need proton transfers in the nucleophilic acyl substitution mechanism. It's possible to need up to 3 proton transfers. We could need a proton transfer prior to nucleophilic attack. This is likely under acidic conditions. If our leaving group is a poor leaving group, we might need to proton transfer to make it a better leaving group prior to loss of a leaving group. And at the end of loss of a leaving group, if the substrate formed is not neutral, it may require a final proton transfer to make a neutral substrate. When you're drawing mechanisms, you're going to need to decide how many and when to use proton transfers. Let's look at another example. Let's take an acid chloride, which again we know is a fairly reactive carboxylic acid derivative, and react it with water. This is actually a fast reaction, even though water and the acid chloride are neutral, because the positive charge of the carbon of an acid chloride is very significant, and this carbon is very electrophilic. And as a result, it's pretty unstable. So the combined energy of the reactants is fairly high, and the activation energy is lower. So if you just expose an acid chloride to water, you're going to get this hydrolysis reaction to form a carboxylic acid. If you didn't want that to happen, you would need to prevent the acid chloride from being exposed to water. So that's when in the lab you might see instructions to weigh out and use the acid chloride quickly because it needs water in the air. And we would also probably carefully use anhydrous conditions to prevent this reaction from occurring if we did not want it occurring and instead wanted the acid chloride to do something else. So let's look at how the nucleophilic acyl substitution would take place. Again, we can have direct nucleophilic attack of water on the acid chloride substrate. And this can occur even though we have a poor nucleophile because the electrophile is very reactive and unstable. That forms a tetrahedral intermediate. The leaving group is chloride, and it is a better leaving group than water, which is why it's getting kicked out here. It's already a good leaving group. We don't need to do a proton transfer, so we can just go ahead and directly do loss of a leaving group and regenerate the carbonyl in the same step. But because the product after loss of a leaving group is not neutral, we do need a final proton transfer to synthesize and isolate a carboxylic acid. So again, we don't need proton transfer initially because we're not under acidic conditions. That's when we would proton transfer to protonate the carbonyl is under acidic conditions. We don't need proton transfer prior to loss of a leaving group because we have a good leaving group, but we do need a final proton transfer in order to make the product neutral. So this pattern is typical for the reaction of acid halides. Nucleophilic attack, loss of a leaving group, followed by proton transfer. You may want to draw out the typical pattern for other functional groups as well, just to try to organize and get a handle on the different mechanisms presented in this chapter. Let's do a practice problem. This problem asks you to propose a plausible mechanism for the following transformation. So in this case, we're reacting an acid chloride with excess ammonia and isolating an amide. Go ahead and pause it, and then we'll go over the answer. Okay, let's go over the answer to this. So recall that acid chlorides are very electrophilic and very reactive. We typically would not treat an acid chloride with an acid because we already have a great electrophile. We don't need the acid to make an even better electrophile. I'm going to go ahead and throw in the lone pairs here because I'm drawing a mechanism, and then add in some ammonia with the lone pair on the nitrogen. So we're going to do a direct nucleophilic attack as it matches the pattern for acid chlorides. Excuse me, I got a little crazy and tried to make a carbon with 5 bonds, but fortunately I realized that that is totally unreasonable, so I just corrected the structure really quickly. Okay, so once we do nucleophilic attack, we are going to get our tetrahedral intermediate, which will undergo loss of a leaving group. Chloride, again, is a great leaving group. It can leave, and then we can use a resonance error to get to the most stable resonance contributor in one step and regenerate the carbonyl. Loss of a leaving group kicks out chloride, and we end up with a substrate that is not yet neutral. So we need to do a final proton transfer in order to isolate a neutral product. You might be tempted to use chloride as your base to do your proton transfer, but recall that we have excess amine and that the nitrogen in ammonia is much more nucleophilic and basic than chloride. So it's much more likely that the ammonia will deprotonate and we'll end up with the amide product and also a byproduct of an ammonium ion. All right, let's get back to our slides. Again, if you want more practice drawing mechanisms, you can practice with Skill Builder 20.1. Okay, so let's talk about the synthesis of acid chlorides. Acid chlorides are produced from carboxylic acids using thionyl chloride. Byproducts to this reaction are SO2 and HCl. I'm going to just put in a note here that says the mechanism that I draw is slightly different than the book. And the reason I propose a mechanism that's different from what Klein proposes is explained in my video. So you can go ahead and access this on YouTube using this link through the PowerPoint slides or just directly. Okay. Acid chlorides, again, are very, very electrophilic and very reactive. So we talked about the fact that if we treat it with water, we are going to synthesize a carboxylic acid. So the mechanism, I believe this was shown before. Did I go the wrong direction here? Or do I just have it in here twice? Possibly I have it in here twice. Either way, we can go over it again. Acid chlorides react with water because this is reactive. We're going to do a nucleophilic attack even with our weak nucleophile. Kick out chloride, followed by proton transfer to achieve the carboxylic acid. This is not a reaction that typically most people want to do, but it's sort of a side reaction that can occur if you expose acid chloride with water. The reason why people would not want to do it is because think about how they must have gotten the acid chloride in the first place. Acid chlorides are synthesized from carboxylic acids using thionyl chloride. So if you took the trouble to treat a carboxylic acid with thionyl chloride to produce an acid chloride, why would you want to go back, right, using water to a carboxylic acid? Typically, you would then use your acid chloride to synthesize something else, So this is, again, usually not a desirable reaction, more of a side reaction that can occur with water and an acid chloride. Sometimes you'll notice that pyridine is mentioned as one of the reagents. Pyridine is a amine-based non-nucleophilic base, and it is used to react with HCl if HCl is formed as a byproduct in the reaction, in order to essentially neutralize it and make it much less acidic. And it's sometimes referred to as mopping up the HCl byproduct. So if you were trying to do this reaction, you might throw in some pyridine to prevent the formation of HCl as a byproduct. Okay, more common than treating an acid chloride with water to form a carboxylic acid would be treating an acid chloride with an alcohol and an equivalent of pyridine to form an ester. The reaction is going to work pretty much the exact same way water reacts with an acid chloride, and alcohol can react with an acid chloride. And again, pyridine is there to mop up the HCl byproduct. Interestingly, sterically hindered alcohols react with acetyl chloride more slowly than less sterically hindered alcohols. So we can actually do a selective acylation of the primary alcohol in the presence of a secondary alcohol using one equivalent of acyl chloride with pyridine. If you want to see the mechanism of a acid chloride being reacted with an alcohol, I have made a separate video of that, and you can use this link to watch that video. Let's talk about the synthesis of amides. The most common way to synthesize an amide is from an acid chloride, because the acid chloride will react the fastest with amines due to their enhanced electrophilicity. When we use an amine to synthesize an amide using an acid chloride, typically we use 2 equivalents of the amine, as long as it's a relatively inexpensive amine and it's not precious to you. One will act as a nucleophile and one will act as a base in the reaction. If the amine was very, took you weeks to synthesize and is very precious, we would not want to waste an equivalent to act as a base, in which case you could potentially use an equivalent of amine and an equivalent of pyridine. Again, pyridine is non-nucleophilic, so the other amine will definitely act as the nucleophile to produce the amide, and the pyridine will act as a base to mop up the HCl byproduct. Notice that if you want what's called a primary amide, we're going to use ammonia. If you want what's called a secondary amide, again, 2 carbons attached to this nitrogen, that's how I generate that term, we're going to use a primary amine, and secondary amines produce tertiary amides. So that means tertiary amines do not react. I have a mechanism or a video showing the mechanism of amines with acid chlorides to produce an amide, and you can access that via YouTube. Acid chlorides can also be reduced using lithium aluminum hydride, and it will synthesize a primary alcohol. We are going to need 2 equivalents of lithium aluminum hydride, so it's common to use or see excess written over the arrow. The mechanism is entirely analogous to an ester reacting with LAH, which you saw before in the chapter 12 on alcohols. But if we take an acid chloride, we can see the nucleophilic attack from the hydride of LAH, followed by a resonance arrow to make our tetrahedral intermediate. Chloride's a fantastic leaving group, so it can leave to regenerate a carbonyl, exposing an aldehyde intermediate. Aldehydes are electrophilic, similar to acid chlorides, and are susceptible to nucleophilic attack by the hydride of LAH. This uses our second equivalent of LAH to produce a primary alkoxide, which can get protonated during the acidic workup. So again, this is the same mechanism as you would see with an ester. The difference is the leaving group, right? We have chloride as a leaving group instead of an alkoxide, which you would have had with an ester. You can synthesize aldehydes directly with using a different hydride reducing agent from acid chlorides. And this is really significant because if it's successful, it can cut down on some synthetic steps. Because you might imagine previously, if we have an acid chloride and we wanted an aldehyde, you could do a two-step process where you reduce the acid chloride to a primary alcohol using LAH, followed by oxidizing the primary alcohol to an aldehyde using PCC. So you could synthesize the aldehyde in two steps, or you could just synthesize it directly. Instead of using LAH, we're going to use a much more selective reducing agent in this tri-terbutoxy aluminum hydride reagent. This is much more selective for the reduction of the more electrophilic acid chloride, and it does not then react with the less electrophilic aldehydes. So it essentially stops at this aldehyde intermediate, and the subsequent reduction of the aldehyde does not occur, and we're able to synthesize the aldehyde directly, which can save some time synthetically. Another reaction that we can do with acid chlorides is treat them with a Grignard reagent. Again, this reaction is very similar to the reaction of an ester with a Grignard reagent, or even an acid chloride with LAH. You can see a lot of parallels with that mechanism as well. Let's look at our acid chloride. Again, we know it's very electrophilic at this carbon, so Grignard reagents can do a nucleophilic attack. We can get our tetrahedral intermediate, which can undergo loss of a leaving group to regenerate the carbonyl and kick out chloride. Now we have a neutral ketone intermediate, but as you know, ketones are also electrophilic and will react with Grignard reagents. So a second equivalent of Grignard reagent will do a nucleophilic attack, leaving an alkoxide that can be protonated under the acidic workup. So again, in summary, acid chlorides react with Grignard reagents, and you need at least two equivalents, so it's common to see excess Grignard reagent to form a tertiary alcohol where we've incorporated two of the same alkyl group from the Grignard reagent. An interesting reaction from acid chlorides is the treatment with a Gilman reagent. A Gilman reagent is kind of similar to a Grignard reagent, except for it's much less reactive. If you look at the difference in electronegativity between carbon and copper, you'll see that it is much smaller than the difference in electronegativity between carbon and magnesium. As a result, this carbon does not have as much negative character as you would see with a Grignard reagent. So it's an organometallic compound where instead of magnesium, we're using copper, and it creates a nucleophilic carbon, but it's much less nucleophilic than a Grignard reagent. But the fact that it's much less nucleophilic is not necessarily a bad thing, because if it's less nucleophilic and less reactive, sometimes that leads to selective reactions. So for example, when we treat an acid chloride with a Gilman reagent, we're able to substitute the chlorine for a methyl group and isolate a ketone directly. What would happen if you used a Grignard reagent instead of a Gilman reagent? Recall that a Grignard reagent would do the same thing to produce a ketone, but it wouldn't stop there. The Grignard reagent would continue to react with the ketone, leading to the eventual production of a tertiary alcohol. So if you don't want to get a tertiary alcohol, instead want to just get a ketone directly from an acid chloride, Gilman reagents are very useful to do this. And it works because acid chlorides, again, are very electrophilic at their carbonyl carbon and more electrophilic than aldehydes and ketones. So we can have a selective reaction with the better electrophile. Once we have the lesser electrophile in solution, the nucleophile is simply not strong enough to react with it, and we're able to stop the reaction at this point. There's a figure in your book, figure 20.9, that summarizes the different reactions of an acid chloride. It's a great reaction or summary to look at when you're making your note cards to learn the reagents and the reactions from this chapter. So note that carboxylic acids are converted to acid chlorides using SOCl2, and that acid chlorides are a very useful synthetic intermediate to then access the production of esters, amides, and it can be primary, secondary, or tertiary amides. You can reduce it using LAH to a primary alcohol. You reduce it using the trialkoxy aluminum hydride directly to an aldehyde. You can form a tertiary alcohol using excess Grignard reagent or utilize the Gilman reagent to form a ketone. Let's do a practice problem to start practicing and start to learn these different reagents. So take a minute, pause the video, and come up with the reagents that are necessary to do all of these reactions. And then after you're done with this problem, continue with conceptual checkpoints 2016 through 2018. Okay, hopefully you came up with the use of thionyl chloride to convert a carboxylic acid to an acid chloride. We're going to use the Gilman reagent to convert an acid chloride to a ketone. And just recall that because I wanted a methyl group here, that's why I put the methyl in the parentheses of the Gilman reagent. From an acid chloride, we can get an ester using an alcohol and commonly an equivalent of pyridine to mop up the HCl byproduct. We can also access amides through acid chlorides, and because I wanted a tertiary amide, I used a secondary amine, and I just used 2 equivalents of the amine to avoid using pyridine. It's just simply easier to measure out a little bit extra of your amine than to go grab a second bottle of or another reagent and add an equivalent of pyridine. So that's a common thing to do. Okay, let's move on to anhydrides. Anhydrides, if they're simple, like acetic anhydride, can be synthesized through the extreme heating of the carboxylic acid that it comes from. So for example, acetic acid, when heated up to 800 degrees Celsius, will dehydrate to form acetic anhydride. This really only works to produce this particular anhydride because most carboxylic acids are not going to withstand this type of extreme heating. Another way you could potentially make the anhydride is through the use of an acid chloride with a carboxylate. The carboxylate will act as a nucleophile, do a nucleophilic acyl substitution to get the anhydride. So again, we'll have a nucleophilic attack followed by loss of a leaving group, and that generates something neutral, so we don't need any proton transfers in this mechanism. The anhydride is very similar in its reactivity to the acid chloride. It's actually a little less reactive than acid chlorides, but it has some advantages. One of the advantages is the fact that oftentimes with an acid chloride, the byproduct of a nucleophilic acyl substitution reaction is the production of HCl. We can avoid forming HCl in the reaction mixture if we use an anhydride instead of an acid chloride, because the leaving group will instead be a carboxylic acid and not HCl. So we end up with a byproduct that's much less acidic, which could be advantageous if we're worried about generating a strong acid in our reaction mixture. Here is a summary of the reactions of anhydrides. Notice that it's pretty much the same reactions that you saw with acid chlorides. So you really don't need to learn this separately. Just think to yourself, anything I can do with an acid chloride, I can also do with an anhydride. Acetic anhydride is actually a fairly useful reagent. We can use it to acetylate an alcohol or an amine, and this will produce an ester and an acyl amide. For example, we can see that in the production of aspirin, a key step is using acetic anhydride to acetylate this phenol. And also in Tylenol, we use acetic anhydride to acetylate the aniline, making this amide. Practice some more with book problems and conceptual checkpoint 20.19. Okay, so recall that previously we learned a method to produce an ester, and that was when we were talking about reactions of acid chlorides. We learned that acid chlorides react with alcohols in the presence of pyridine to mop up HCl to form an ester. There are other ways to produce an ester. There are specifically 3 ways. The second way is from, instead of using a carboxylic acid, we can use, an acyl chloride, we can use a carboxylic acid. If we deprotonate the carboxylic acid with a base, such as sodium hydroxide, we'll get a carboxylate ion, which can do an SN2 reaction with an unhindered alkyl halide like methyl iodide. This will end up producing an ester using basic conditions in this case. The third method that can be used to produce an ester is actually has a name reaction, and it's called a Fischer esterification. It combines again a carboxylic acid as its one of its organic reactants, along with an alcohol, a strong acid catalyst. It will produce an ester, and water is a product. Notice the equilibrium arrow with this reaction. So this is a reversible reaction, and if you want to drive the reaction forward, you either use a large excess of one of the reactants or remove water as it's produced in the reaction. When you're drawing the mechanism, make sure that you're drawing a mechanism that's consistent with the acidic conditions employed. Notice that, or just remember that under acidic conditions, it's common to have either neutral or intermediates that have one positive charge. We should not be generating any intermediates with an oxygen with a negative charge. That's very unrealistic under acidic conditions without an amine present. Okay, so let's look at the mechanism of the Fischer esterification. Recall that we're under acidic conditions, but instead of having a lot of water present, we're going to have likely a lot more methanol present. So with the strong acid catalyst and methanol present, our acid in solution is the protonated methanol. We can do a proton transfer to transfer the proton from the protonated methanol to the carbonyl oxygen of the carboxylic acid. That generates a charged intermediate, which is going to be much more reactive and lead to a reasonable activation energy barrier for reaction with a neutral and stable methanol as our nucleophile. So the lone pair on the oxygen of methanol can do a nucleophilic attack, and we will move electrons up to the oxygen in this step. At this point, we have an intermediate that is tetrahedral, and it has a positive charge, right? Remember that we should be having intermediates with either one positive charge or neutral, so this is very consistent with what we would expect for a mechanism under acidic conditions. The goal here, if to synthesize an ester, is to get rid of one of these OH groups as water and keep this oxygen attached to the methyl group. So in order to get rid of this as water, we need to protonate it to make a good leaving group. But we want to avoid any intermediate with more than one positive charge. So first we're going to deprotonate this oxygen and then transfer the proton to one of these 2 oxygens. So we're going to go through a deprotonation followed by protonation step in order to remove this proton and simply move it to another oxygen, which then creates a good leaving group in water So we can go ahead and do loss of a leaving group. And we can use either one of these oxygens to generate a double bond and help kick out water as a leaving group. At this point, we are very close to the product. We just need one final proton transfer in order to get to a neutral product. So we'll just use a molecule of methanol to deprotonate that to get the neutral ester. This will also regenerate our acid catalyst, so we only need a catalytic amount. If you want to see me draw that out step by step, go ahead and check out this YouTube video where I drew out this mechanism by hand. The mechanism for the Fischer esterification reaction is supported by an isotope labeling experiment. Specifically, when they used isotopically labeled methanol, where the oxygen is labeled, they found out that that oxygen is conserved in the product, and it's specifically the oxygen attached to the methyl group. So that's significant because now we know that we actually lose this oxygen to form water and not the oxygen attached to the methyl group. So that helps support the mechanism that we draw for this reaction. Again, the Fischer esterification is an equilibrating process. So we want to remove water, right, from the reaction mixture in order to drive the equilibrium forward. We can also use excess of one of the reagents, such as excess methanol or excess carboxylic acid. Let's do a practice problem. This is a synthesis problem, so it's going to take multiple steps to get from this reactant to this product. Go ahead and see if you can identify the individual steps and reagents needed to accomplish the following multi-step synthesis. Pause it and try to work on the problem. Of course, whenever you're doing this, try to utilize reactions that we were just talking about in the lecture. Okay, let's go ahead and think about how we would do this problem. Right, so one of the things I noticed is that attached to the benzene ring are 2 carbons, right? And right now I know I only need 1 carbon. So I actually know I need to get rid of one of these carbons because it is not present anymore in the product. So that's something to think about. Whenever I want to do a carbon-carbon bond breaking reaction, I often think about potentially doing ozonolysis. So if I do ozonolysis on that alkene, I will end up with an aldehyde. So note that the reagents are ozone followed by a reducing agent like DMS or zinc. Now we just need to think about a functional group transformation, right? I need to transform this aldehyde into this ester. I don't know a way to do that in one step. However, I know I can access an ester either from an alcohol or from a acid chloride. Sorry, not an alcohol, an carboxylic acid or an acid chloride. So perhaps if I can target as a key intermediate a carboxylic acid, I'll then be able to convert that carboxylic acid to an ester. To get from an aldehyde to a carboxylic acid, we simply need to oxidize this carbon. So we can use a strong oxidizing agent such as sodium dichromate. From the carboxylic acid to an ester, we actually have 2 choices, right? There are 2 of the ester forming reactions start with a carboxylic acid. We really have 3 choices, right? Because we could first convert this to an acid chloride and then to an ester, or there's 2 reactions that go directly from the carboxylic acid to an ester. So let's look at the 3 options here, right? We can do the Fischer esterification that utilizes ethanol and a strong acid catalyst, right? And we lose water, so oftentimes over the arrow you'll see minus water, right? So we'll make a little note. This is the Fischer esterification. So it's a name reaction, so I always like to remember the names when I'm writing my reactions. So that's option number 1, or option number 2, directly from the carboxylic acid, we can treat with a base, right, such as sodium hydroxide, followed by, in this case, ethyl with a leaving group, because we're introducing an ethyl group, right? So ethyl bromide or chloride would work. And again, our third option is possibly converting the carboxylic acid to an acid chloride using thionyl chloride. And then from there, I can use ethanol and pyridine to produce the ester. Okay, back to the slides. We can do basic hydrolysis of an ester. This reaction is also called a saponification because it's the key reaction in soap production. From an ester, we treat with sodium hydroxide that will hydrolyze to the carboxylate, and we need an acidic workup in order to isolate a carboxylic acid, because remember, a carboxylic acid under basic conditions will always be deprotonated and negatively charged as a carboxylate ion. So an acidic workup is necessary to produce a carboxylic acid. The mechanism for this, we have hydroxide as our nucleophile, which is a strong nucleophile, so we can do a direct nucleophilic attack without any need for a prior proton transfer. From here, we have about equal leaving groups, right? If we kick out hydroxide or an alkoxide, those have about the same ability to act as a leaving group because they have about the same base strength. So it's reversible, right? If we kick out the hydroxide, we would go straight back here, or eventually we may kick out the alkoxide and move forward in the process. If we move forward and we kick out the alkoxide, we can generate a carboxylic acid. Recall that under basic conditions, carboxylic acids will not stay as carboxylic acids. They will be deprotonated to form a carboxylate salt, which will then we can reprotonate during an acidic workup to isolate the neutral carboxylic acid. This is the driving step of this mechanism. It is the irreversible step because of the pKa difference, right? Carboxylic acids have a pKa of about 5, alcohols have a pKa of about 17, so that's a significant enough difference that essentially the reaction does not go back. If you want to see me draw out this mechanism by hand, check out this YouTube video that I prepared a while back. Okay, esters can also be hydrolyzed under acidic conditions. So the previous saponification reaction is considered the hydrolysis of an ester under basic conditions. We can also treat with water and acid and hydrolyze the ester under acidic conditions. You can think of this as the reverse of the Fischer esterification reaction, because the Fischer esterification reaction combines a carboxylic acid and an alcohol with an acid catalyst to produce an ester and water. So if we wanted to go back, we would use a large excess of one of the reagents. So for example, a dilute acid solution would have a lot of water, and it would promote the reverse, and we would hydrolyze the ester back to a carboxylic acid. Let's draw out the mechanism. Again, we should hit all the same intermediates that we did in the Fischer esterification reaction, but in reverse order. So the ester can be protonated using hydronium ion. We can protonate the oxygen of the carbonyl to form a very electrophilic intermediate. Water can act as a nucleophile to do a nucleophilic attack. Now we need a series of proton transfers to replace the proton on this oxygen with a proton on the oxygen of a different oxygen, in this case, this oxygen. So, we want to avoid any intermediates that have more than one positive charge. So it makes sense to first deprotonate this to get a neutral intermediate and then proton transfer on another oxygen. And again, these are all reversible steps. So protons can be moving around between all of the different oxygens in solution. But once we get here, this is a good leaving group, so it can get kicked out. And now we're very close to the carboxylic acid. All we need to do is a final proton transfer. That also regenerates our acid catalyst. Esters can also undergo reaction with amines to make amides, and you might call this an aminolysis reaction. However, this reaction is not a very useful reaction. Even though it's possible, it's going to require prolonged periods of heating. And the reason why is ammonia is not extremely nucleophilic and esters are pretty stable. So this is kind of a weaker electrophile. This is a weaker nucleophile. So it's going to have a pretty high activation energy to react. So the process is pretty slow, making the synthetic utility of this reaction pretty limited. If you want to synthesize an amide, it makes much more sense instead of from an ester to synthesize it from an acid chloride, which we saw in a previous section of the chapter. We can also reduce esters using excess lithium aluminum hydride to primary alcohols. Again, this mechanism is entirely analogous to the reduction of an acid chloride, right, with LAH. The only difference is instead of a chloride leaving group, we have a methoxide leaving group, but all of the other steps are the same. Nucleophilic attack by the hydride of LAH onto the carbonyl of the ester forms a tetrahedral intermediate. Loss of the methoxide leaving group produces an aldehyde intermediate, which can be further reduced with LAH. So draw a second equivalent of LAH and do a second nucleophilic attack to reduce this carbon further. The alkoxide will wait at this point until you add in a something to protonate it at the end, either water or a dilute acid solution will work. Again, this is not a reversible step, right? Because these are not good leaving groups. What if you don't want to reduce the ester all the way down to a primary alcohol? Wouldn't it be advantageous to, instead of getting a primary alcohol, to potentially stop at this aldehyde intermediate? You can do that, but not with LAH, because LAH reduces aldehydes. Instead of using LAH, what if we use a different hydride reducing agent? The one that works best is called DIBA, which stands for diisobutyl aluminum hydride. And this one is selective for the reduction of esters. Again, that aluminum coordinates to both oxygens to deliver the hydride. This reaction only really works well if you keep the reaction temperature very low, like in an acetone dry ice bath, which generates a temperature of -78 degrees Celsius. If you're able to keep the reaction temperature very low, aldehydes can be produced and it will stop at this point without further reduction. If the temperature creeps up, unfortunately, sometimes the aldehyde then gets reduced to a primary alcohol and the reaction produces a mixture. So this is actually a very tricky reaction for an organic chemist to perform. Another review reaction, recall from the alcohol chapter that we can produce tertiary alcohols from esters using Grignard reagents. And because we're going to incorporate 2 equivalents of the Grignard reagent, we do need excess Grignard reagent followed by a water or acidic workup. The mechanism should be reviewed for you, but let's go ahead and go over it. From the ester, if we're treating with a strong nucleophile like a Grignard reagent, it can do a direct nucleophilic attack on the carbonyl of the Grignard, forming the tetrahedral intermediate that can undergo loss of a leaving group, producing a ketone. Recall that ketones are electrophilic and are reactive with Grignard reagents. So a second Grignard reagent can do a second nucleophilic attack, now producing a tertiary alkoxide, and then eventually, once water or acid is introduced in the reaction, we'll be able to isolate the neutral alcohol. You want to practice drawing these mechanisms. Check out conceptual checkpoint 20.22 and 20.23. Let's do a practice problem. See if you can come up with the reagents for all of the arrows here that are missing their reagents for these 4 reactions. Go ahead and pause it and do your best to come up with the reagents, and then we'll talk about it. Okay, so you might have recognized that in this direction, we are essentially converting a carboxylic acid and an alcohol to an ester. So this is really just a Fischer esterification. But the 2 components, the alcohol and the carboxylic acid, are tethered to the same molecule. So this is an intramolecular Fischer esterification reaction. We do need a strong acid catalyst, but because water is a product, we would want to use concentrated sulfuric acid. And then there's a driving force to produce more water to then dilute this acid solution. From the ester, or in this case, cyclic esters are actually called lactones, but functionally it's the same as an ester. Okay, so from the ester or lactone, if you want to go back to the carboxylic acid and water, we call this a hydrolysis reaction because we're actually incorporating water into the reaction to produce the product. So because water is a reactant, we would actually like to have excess water in the reverse reaction. So we'll use a dilute strong acid solution. Okay, from the same ester or lactone, what if you wanted to get to an aldehyde, right? So you can use, again, you can use DIBA for that. If you use LAH, recall that it would reduce this all the way down to a diol. If you want to synthesize a tertiary alcohol, right, from an ester or lactone, we can use Grignard reagent. Because we're incorporating 2 methyls into the molecule, we're going to use excess methyl magnesium bromide followed by water or a acidic workup to protonate the diol. All right, let's start talking about amides. Amides can be made from any of the other carboxylic acid derivatives. Because it's the least reactive and most stable, we are always essentially doing an exothermic reaction when we convert one of these other carboxylic acids derivatives to an amide. But the reaction that is most favorable is from an acid chloride. So commonly, if somebody wants to produce an amide, they would likely use an acid chloride just because it's going to produce the fastest reaction and probably the highest yield. So again, the most popular way to make an amide is from an acid chloride using the corresponding amine. If I want to make a primary amide, I would use ammonia. And I can either use 2 equivalents or 1 equivalent of ammonia and 1 equivalent of pyridine. One, again, will act as a nucleophile, the other acts as a base to mop up the HCl byproduct. From an amide, let's talk about reactions that we can do from an amide to make other functional groups. Well, we just talked about the fact that we would make an amide from an acid chloride, which is made from a carboxylic acid. So this is sort of going in one direction. We would treat the carboxylic acid with thionyl chloride to make an acid chloride, then treat the acid chloride with ammonia to make the amide. But if we want to go back from an amide to a carboxylic acid, we need to do a hydrolysis. We can either do a hydrolysis with acidic conditions or basic conditions. So you'll either see hydronium ion or hydroxide ion as the reagent. Either way, the reaction requires a lot of heat. Recall that amides are very stable and much more stable than the other carboxylic acid derivatives, including the carboxylic acid. So this is going to be very endothermic, and we are going to need an extreme amount of heat to climb that energy barrier. So this is a very slow process. Let's look at the mechanism under acidic conditions of amide hydrolysis. If we're treating with acid, it makes sense to protonate the carbonyl. This will give us a more electrophilic carbonyl carbon, which is very useful in this case because, again, amides are so stable. So we definitely need to protonate it to make it more reactive. At this point, water can act as a nucleophile to do a nucleophilic attack, and a series of proton transfers will transfer this proton from the oxygen to the nitrogen. Once we're at a point where the nitrogen is positively charged, it's a good leaving group, and it can get kicked out. We can use one of the lone pairs on one of these two oxygens to help kick it out in the generation of this double bond. And then we can either use water or the more basic ammonium ion to do our final proton transfer to isolate the neutral carboxylic acid and ammonia. If you want to see me draw this mechanism out step by step and talk about each step in detail, check out this YouTube video that I prepared previously. Recall I mentioned that amides can be hydrolyzed under both acidic and basic conditions. So these are how you would write the reagents to do a basic hydrolysis. Actually, basic hydrolysis is even slower than when acidic conditions are used. So this is not a reaction that's performed very often, but it's possible to do it if you heat the reaction for an extended period of time. Again, we're going to need an acidic workup because we cannot isolate a carboxylic acid under basic conditions because of the fact that the carboxylic acid is acidic and it would react with the base to form a carboxylate salt. The mechanism, when we do a strong nucleophile under basic conditions, we don't need a first proton transfer. So we just do direct nucleophilic attack on the carbonyl. Loss of the NH2- leaving group. Notice our intermediates under basic conditions have negative charges, right? First an oxygen with a negative charge, eventually a nitrogen with a negative charge. This is a very fast reaction. As soon as we isolate a carboxylic acid, it will immediately undergo deprotonation by the leaving group that we just got kicked out. And this is essentially irreversible because of the very significant pKa difference between the acid and conjugate acid. The acid has a pKa of about 5, and the ammonia has a pKa of about 35. So with a difference in 30 pKa units, this is an irreversible reaction. If you want to see the mechanism drawn out more slowly, check out this YouTube video using the link on this slide. So we can also reduce amides using LAH. It does take excess LAH as we are going to incorporate 2 hydrides from LAH, but unlike reduction of the other derivatives of carboxylic acids, in this case we're not going to produce an alcohol. So recall that when we use the other derivatives of a carboxylic acid, we always produced a primary alcohol when we reduced with LAH. But in this case, we actually reduce an amide and get a primary amine. So the mechanism is actually quite different from the other LAH reduction mechanisms in this chapter, and it's actually beyond the scope of the class, so we're just going to skip it. All right, let's do a practice problem. I would like you to try to identify reagents that can be used to accomplish the following multi-step synthesis. And I'll always be sure to show isolated intermediates. So go ahead and pause the video and see if you can come up with a series of reagents to do this transformation. After you're done doing this practice problem, check out conceptual checkpoint 2024 and 2025. Okay, let's go ahead and go over how to do this. So it looks like when we're looking at the carbon backbone, we have the benzene and one carbon outside of that benzene ring. And that's consistent with the product as well. So we don't need to lose or add any carbons, which is useful to note when we're doing this practice problem. What we do need to do is essentially a functional group transformation. We need to string a series of reactions together that will allow us to convert a carboxylic acid to a primary amine. So one of the reactions that we just talked about is actually the synthesis of a primary amine through the LAH reduction of a primary amide. Right? So if we had synthesized an amide, we would be able to reduce the carbonyl using excess LAH and an aqueous workup. So now we just need to think about how would I convert a carboxylic acid to an amide. And again, the most common way to get an amide is from an acid chloride. So if I had an acid chloride, then I would treat with excess ammonia to get to this primary amide. And then that just leaves the conversion of the carboxylic acid to the acid chloride, and we need thionyl chloride for that. All right, let's go back to the slides and talk about the last functional group in this chapter, nitriles. So first we're going to talk about how to prepare or synthesize a nitrile. So recall that we've seen the synthesis of a nitrile before when we looked at SN2 reactions from alkyl halides using sodium cyanide. Recall that when you use an SN2 reaction, you need an unhindered alkyl halide. So this carbon is most preferably primary or methyl. Another way to synthesize a nitrile is through the dehydration of an amide, primary amide, using thionyl chloride. So we can actually convert an amide to a nitrile using thionyl chloride, as well as the conversion of a carboxylic acid to an acid chloride. So whenever you have a reagent you've seen before, it's always useful to side-by-side compare reactions using the same reagent. So go ahead and write in your notes, we can use SOCl2 to convert a carboxylic acid to an acid chloride, as well as a primary amide to a nitrile. Does anybody see the difference in these two reactions? Any differences? You can go ahead and pause it and test yourself to see if you can identify any key differences. Okay, so what hopefully you might have come up with, if you thought about it, was the fact that, remember we talked about the fact that this reaction is a one carbon homologation reaction. So we're actually adding a carbon to the carbon chain, which is something we want to take note of. From a amide, doing the conversion to a nitrile, we do not add a carbon, right? So we maintain the same carbon backbone. So depending on if you're, for example, trying to synthesize a nitrile, ask yourself, do I want to add a carbon as I synthesize this nitrile, or do I want to keep the carbon backbone the same? And that might actually help you figure out which reaction to use. In addition, there is no limitation on this R group. It does not need to be unhindered primary or methyl, right? Whereas we definitely need an unhindered alkyl bromide to do an SN2 reaction, right? So there's some limitations on the overall alkyl group here, and this could be anything. So those are two key differences to take note of with these reactions. Let's look at the mechanism of the reaction of a primary amide with SOCl2 to form a nitrile. So if you draw out the resonance contributors of an amide, you'll see that the nitrogen has a partial positive charge and the oxygen has a partial negative charge. So it makes sense that the oxygen is more nucleophilic than the nitrogen, and it will be the atom that does the nucleophilic attack on the sulfur of the thionyl chloride. Once that happens, we can do a second step where we lose chlorine as a leaving group to regenerate a double bond here, this time between sulfur and oxygen. Usually a base like pyridine is incorporated into this reaction, and if it was there, it would act as a base to deprotonate the nitrogen. If you don't have any pyridine there, then chloride can act as the base to deprotonate this nitrogen, since you just kicked it out, but then that generates HCl in solution, which might be avoided by introducing a base like pyridine to the reaction mixture. We can then use a second equivalent of base to deprotonate the nitrogen again, in this case now generating a triple bond between this carbon nitrogen and kicking out SO2 and chloride. If you want to see this mechanism drawn out more slowly, check out this YouTube video. Okay, what can we do with nitriles? Well, we can do hydrolysis. We can do acidic hydrolysis and basic hydrolysis. And it's really similar to the hydrolysis of an amide because we actually produce an amide en route to a carboxylic acid. So regardless if you're under acidic conditions or basic conditions, the hydrolysis of a nitrile goes through a primary amide and then gets further hydrolyzed to a carboxylic acid. This step in particular requires extreme heat. The mechanism, we're just going to talk about the mechanism from the nitrile to the primary amide, because you can look back in the slides or your notes to look at the hydrolysis of an amide to a carboxylic acid. From the nitrile, there's a lone pair on the nitrogen that can get protonated under acidic conditions. That generates a much more electrophilic carbon here, which can then be attached. I'm actually going to take a break here because I'm getting some phone calls. So I'm going to stop sharing, pause the video for a sec. Okay, sorry for the interruption. Let's go back to the mechanism. So after water has done its nucleophilic attack, we get this intermediate. Again, notice that the intermediates have a positive charge. None of them have a oxygen with a negative charge, which would be very consistent with acidic conditions in terms of mechanisms. What we want to do now is essentially move a proton from the oxygen to the nitrogen. What we're going to do is use water to deprotonate and then reprotonate the nitrogen, allowing us essentially to tautomerize this to a constitutional isomer, which is drawn as two resonance contributors here. When you see this resonance contributor, you can see how close you are to the amide. All you need to do is one final proton transfer to get to the amide. And again, if you continue heating in the presence of water and acid, you can further hydrolyze this to a carboxylic acid, although again, that process is very slow and requires high heat. If you want to watch the mechanism of the hydrolysis of a nitrile, go ahead and check out this video, where I've drawn it out in more detail and more slowly. Okay, nitriles again can also undergo basic hydrolysis. Similar to the fact that you might recall amides and esters undergo both acidic and basic hydrolysis, nitriles undergo both acidic and basic hydrolysis, and it still goes through an amide intermediate and eventually gets to a carboxylic acid. You do need an acidic workup whenever you're isolating a carboxylic acid, and because it will not be isolatable under basic conditions. Let's look at the mechanism. When you're using hydroxide as a nucleophile, you can do a direct nucleophilic attack. That gives us this intermediate with a negative charge, which is very consistent with basic conditions. A nitrogen with a negative charge is very basic, so it should be able to pick up a proton from water. Once we get here, we're at a neutral species, but the goal is to get to an amide and then eventually a carboxylic acid. We're under basic conditions, so we can continually deprotonate, in this case, the hydrogen on the oxygen atom. That gives a negatively charged oxygen atom. If we want, we can draw resonance at this point, and that allows us to see how close we are to the amide. All we need to do is do one final proton transfer to neutralize this nitrogen and get to the neutral amide. Again, we can continue with the basic hydrolysis of the amide to get to a carboxylic acid. Go ahead and look back in your notes or at the slides to visualize that mechanism. You can also view the mechanism that I drew out on YouTube. What else can you do with nitriles? Well, it turns out, and this is a very synthetically useful reaction, that if you treat a nitrile with a Grignard reagent, you can isolate a ketone. You should be thinking that this is a very unique reaction, because typically, if you get a ketone in solution with a Grignard reagent, they're going to react together, right? We know that we can treat ketones with Grignard reagents to form alcohols. So you might wonder, how is it possible that they can stop at a ketone and that the ketone will not react with the Grignard reaction in solution? And the answer is because when you treat a nitrile with a Grignard reagent, the Grignard reagent is very, very nucleophilic. So of course it will do a nucleophilic attack on the carbon, pushing electrons from the pi bond up to the nitrogen. And then you're stuck at this intermediate and ask yourself, what can we do with this intermediate? There is no leaving group. Normally you would do loss of a leaving group, but both of these are alkyl groups and are not good leaving groups. So essentially it's stuck like this until you add in your water workup. When you add in acid and water for the workup, you'll protonate this and get an imine. And as you know, imines can be converted to ketones under acidic conditions. But at that point, once you've added the acid, you've quenched any excess Grignard reagent. So your ketone is only exposed in solution once there's acid around, and when there's acid around, there's no more Grignard reagent. So you can isolate a ketone in this case because we have quenched the Grignard reagent by the time the ketone is in solution. You can reduce nitriles using excess LAH. Again, both of these hydrogens or hydrides will come from LAH. And again, it will give you a primary amine similar to an amide. So at this point, because we've done a lot of reductions with LAH with a lot of different carboxylic acid derivatives and also aldehydes and ketones, it's useful to take a moment to organize our reactions, right? So a lot of times when I organize reactions and want to learn reactions, it's helpful, for example, to write out all of the different LAH reduction reactions that I've learned. So starting from amides and nitriles, but also all of the other carboxylic acid derivatives, take a moment to organize the reactions so you can see them all together. And when you do that, your brain helps you remember the patterns. So hopefully you did that. And if you didn't, I've done it for you. So here's a summary of the different reductions using lithium aluminum hydride. So with both a primary amide and a nitrile, when we reduce with LAH, we get a primary amine. That's very different from the other carboxylic acid derivatives, including a carboxylic acid, an acid chloride, and an ester. When we reduce those with excess LAH, or in this case, actually you do need excess LAH in this reaction too. I'm not sure why it doesn't say that, because the first equivalent, deprotonates and then the Al3 reacts. So sorry, you only need one equivalent in this case. Anywho, regardless if you need more than one equivalent or not, when you reduce a carboxylic acid, acid chloride, and ester, you get a primary alcohol, which is different than a primary amine. And I also threw this reaction in there just to remind you that LAH also reduces aldehydes to primary alcohols, and ketones to secondary alcohols. And you can go ahead and add that if you'd like to the summary chart. You can continually practice reactions by doing checkpoints 20.27 and through 20.29. Let's talk about synthetic strategies. So we're always going to stick with the same strategy when we're discussing synthesis. Ask yourself, in the synthetic change, is there a change in the carbon skeleton? Meaning, did we add or lose carbons? That's important to know. Or are we just doing a functional group transformations, right? There are a lot of functional group transformations in this chapter because we just studied 5 different functional groups in one single chapter. This slide kind of shows a summary of different functional group transformations. It's kind of busy and my brain doesn't work by absorbing this giant of a slide, but you could use it to remember all the different ways that different functional groups can be converted to each other. Okay, so in this particular chapter, there's a couple of different kinds of carbon-carbon bond forming reactions. So if you are needing to make a new carbon-carbon bond, you want to think about which reactions you should probably be utilizing. One is the use of a Grignard reagent, which is something we've looked at a lot. We can use Grignard reagents with acid chlorides and esters to produce tertiary alcohols. Also, Gilman reagents. Gilman reagents are very, very useful. They convert acid chlorides to ketones. So it's something, because we, of course, know a lot of different reactions of ketones like acetal and enamine reaction and stuff from the previous chapter. This is a great bridge from chapter 19 to chapter 20. Right, we can synthesize ketones, and then chapter 19 tells us all the different ways we can react to ketone to form other things. Also very, very useful is the reaction of a nitrile with a Grignard reagent to form a ketone directly. Again, another great bridge from this chapter to the previous chapter. We also did 1-carbon homologation reactions to form either a nitrile or a carboxylic acid, using sodium cyanide followed by hydrolysis or Grignard with CO2. So those also expanded the carbon chain. So it's really important to keep those reactions in mind when doing different synthetic problems from this chapter. Okay, it's also important to recognize and also keep in our mind previous reactions, such as the formation of a Grignard reagent in reaction with an epoxide that we previously covered in chapter 13. That actually introduces the functional group 2 carbons away from the new carbon-carbon bond, right? So this is very different from the reactions in this chapter, but it's good to have it in our mind, different reactions that we can use to, because there's so many reactions, and organizing them will really help us keep everything straight. Okay. Let's do a couple of practice problems with different multi-step syntheses. And so the practice problem asks you to identify reagents that can be used to achieve each of the following transformation, and make sure to utilize at least one reaction from this chapter. And I put that in there because, of course, you might think of ways to convert this alkyl halide to this ketone using reactions from previous chapters, and that's great. You definitely can do that. But we want to identify a synthesis that uses at least one reaction from the chapter as well as an alternative to that other method. So go ahead and pause and practice or see what you can come up with, and then we'll talk about it. Okay, so let's go ahead and work through these problems. So if we look at the first practice problem, we have the carbon backbone is not changing, right? So we have the benzene, again, 1 carbon outside of the benzene ring, and we still have 1 carbon outside of the benzene ring. So this is essentially just a functional group transformation only, no need to add or lose carbons in this case. So then it's a question of, okay, what reactions do we need to string together to go from a carboxylic acid to a nitrile? We cannot do that in one step, but there are pathways that we can take advantage of using multiple steps to get there. Okay, so remember that if we want to synthesize a nitrile and we don't want to add any carbons, then we need to get that nitrile through reaction of a primary amide with SOCl2. Right, so there's two ways to make a nitrile, but there's only one way that is useful in this particular synthesis problem, and that's the reaction or the dehydration of a primary amide to a nitrile using SOCl2. So then you might ask yourself, how can I get from a carboxylic acid to an amide? And typically people synthesize amides again from acid chlorides. So if we convert the carboxylic acid to an acid chloride, we'll be able to synthesize an amide. So again, SOCl2 is used for both the conversion of an acid to an acid chloride and an amide to a nitrile. And from an acid chloride to an amide, we're going to use excess ammonia. Okay, let's look at the other synthesis. And again, I said that we want to utilize at least one reaction right from this chapter. So even though you could just form a Grignard, treat with an aldehyde, and then oxidize the alcohol to a ketone, that's not the synthesis that we're trying to go for in this chapter. But just to remind you of how that would work, right, we would take an alkyl halide, treat with magnesium to form the Grignard reagent, and then treat with a aldehyde. And again, we're going to add in 3 carbons here, right? We're making this carbon-carbon bond. So I'm going to use an aldehyde with 3 carbons, right? Followed by an aqueous or acidic workup. That would get me to a secondary alcohol that I could then oxidize to a ketone using PCC. But the problem is that this did not utilize a reaction from this chapter. So what are some of our alternatives here that do utilize reactions from this chapter? Okay, so what if we, starting from an alkyl halide, I kind of remember that I might be able to make a nitrile, right, from using sodium cyanide, right? So what if instead I try to utilize a reaction from this chapter and end up with a nitrile, right? That's actually very helpful because I know that I can convert a nitrile to a ketone directly using a Grignard reagent, right? So I want to add these 2 carbons now, and so I'm going to add in an ethyl Grignard reagent, right, followed by a hydrolysis of the resulting imine to a ketone. So again, I can go, using a Grignard reagent, I can go directly from a nitrile to a ketone. So that pathway utilizes reactions from this chapter. Let's go back to the slides here. And oh, looks like we're done. So hopefully, I know that's a lot of information, and I think the video is over 2 hours, but hopefully that gave you a good introduction and you can now practice your skills on the activities.